Hi, welcome to Dante's programming channel. My name is Dante, known to many as Claire. That's also my name. And I created a Gmail account for like business purposes, and so now I guess I have a YouTube channel too. So I'm gonna use it to show off my projects. So today I want to show you guys a project that I made called the TMA16. So the TMA16, what it is it's a virtual machine that I implemented in Rust, and it uses an instruction set architecture of my own design. So it's basically a hardware emulator. It's just there's no actual hardware version of it, but yeah. It's a reduced instruction set architecture. It's only got 32 instructions. It has 32 like basic instructions, but it has variable length instructions. So if I show you something in the specification that might clarify that a bit. So the first byte specifies the instruction, and then subsequent bytes are operands to that instruction, and each instruction includes, like, unless it's just a jump instruction, each instruction implicitly has how far in memory to jump, so that it's not trying to execute these data values as though they were instructions, because they're probably not valid instructions, and if they are, they're definitely not the ones we want to execute. But so, yeah. Reduced instruction set architecture with variable length instructions. That's kind of a very, very weird design choice. And also you can see there's many ways I could have done it similarly, but had it been a lot more efficient. Like here I've got 0 and 0. There's no need for those zeros to be there. I could have just packed these two 4-bit values together, but this is what we got. So yeah. It also has an assembler, which is 70% written by me, 30% written by this guy on GitHub who made a bunch of improvements to it and wrote some tests for it for Hacktoberfest. It's written in Python. It's probably could be a lot better written, but it works pretty well. And it's a lot better written than it used to be, believe me. It used to be a pile of hot garbage. But, well, this part's kind of embarrassing. Parsing escape characters like this. It's very, very embarrassing. Very not DRY. But other than that, I'm pretty happy with the rest of the assembler. And here it implements the instruction set, matching the assembly tokens to the corresponding machine code byte. Yeah. So, enough rambling about the TMA16. Let's see it running some programs. So, the default extension for it is TMX. And you can include a delay, so like you can tell it to wait, say for example 64 millis, and what this will do is it'll make it so it'll put a 64 millisecond delay between the execution of each instruction. Because, and then here you can see it's printing out hello world, because the whole idea of this is to make it easier to visualize low-level computation by having a diagram of the CPU's state. So, like you can see what's in these registers. There are 4 16-bit registers. You can see their contents both in binary and hexadecimal. And you can see the stack, which is 32 bytes, but you can only push and pop it 2 bytes at a time, because each of these little values here is 16-bit. And here's your instruction pointer, which tells you where in memory the currently executed instruction is, and then what the first byte of that instruction is. Then you can also have no delay. You could also suppress the animated diagram, in which case it will run really fast. Like, it'll run like comparable to bare metal C. It'll run comparable to C. Not as fast as C, but like less than 20 times as slow as C, if that makes sense. So it's a pretty efficient runtime, and that comes from it being written in Rust. And I'm using the release compiled version right now, not the debug version, which is probably a lot slower. Is a lot slower. I've benchmarked it several times. And if I run it in Valgrind, it should have no memory leaks. Because the Rust compiler is really good about making sure memory leaks don't happen. Now, I know that you can still cause memory leaks if you're being foolish, but this implementation, haven't encountered any so far. Then it's also got input is implemented, so I could type stuff in. So it's gonna first print out a prompt. It's fun to watch the registers get different values moved into and out of them. And then it's halting execution, waiting for me to type something in. So every character I press, it will immediately put onto the stack. Although right now it's got a null character at the bottom of the stack. You can't see it right now, but if I say H, now you can see null character, hexadecimal H. Then I could do something to like pack the characters in here, since these are 16-bit. That would take many more clock cycles, but it would give me a lot more stack space to work with, since this is only 32 bytes. The stack is actually really weird because it's not part of main memory. It's built into the hardware. And then I press enter and it will print it back out. And why don't we go through the source code of the program that I just ran. It's written in TMA16 assembly. And I use Nano because I wrote my own syntax highlighting file for TMA16 assembly in Nano. So let's go through and see what happens. So it's jumping to main, because right here it's going to include this. It's going to include print.asm, and we don't want to right away execute the instructions in print.asm, because what this include will do is it'll just find the contents of this file and copy paste them verbatim at this point before, like, in the process of assembly. It's not like it's creating a new assembly file, but while it's assembling, it'll put this file's contents right here. And so that's why we have to skip over them. So we go to main, and here we're putting the arguments for print string on the stack. So here we want to put the return address, so where we want to jump back to when print string exits. And we also want to put a pointer to the string that we want to print, which is defined down here. Yeah. So it'll print out the prompt, and then after that it'll get to here, because that's what we passed to it for the return address. And so what we'll do then is they'll push register D, so all the registers are initialized to 0, and we haven't set this to be anything else, and neither does print string, so that'll just be a null character. It'll be 0 on the bottom of the stack. Then we'll put a new line character in register B, so that we can check to see when the users pressed enter by comparing whatever they pressed to that. So then what it'll do, we have a single instruction for getting input. It's just get. So it'll wait for the user to press a key, and whatever the value corresponding to that key is, it'll get stored in register A, or whatever specified register. We could change this if we wanted. And then out is a single instruction for printing that character to standard output. So out and get are how you do I/O in TMA16 assembly, which is way easier than any assembly language I've heard of. So then jump if equals register A, register B. So if whatever the user just typed in is a new line, then jump to output, which is down here. Otherwise, push whatever they typed onto the stack and then jump to input loop. And so once we get to output, what it'll do is it'll just print the characters out one by one, basically. And then what it'll do after that is it'll print a new line so that our prompt doesn't look weird. Like when we go back into the bash shell, the prompt won't be right after the last thing it output, and it'll halt. And then our prompt is declared down here, and \s stands for space because the assembler breaks up tokens by white space. So if I had a space inside of a string literal like that, it would interpret L quotation mark and then this quotation mark as 2 tokens. And it wouldn't know what to make of this because that's not a valid TMA16 assembly token on its own. So use \s instead. And then down here we've got our null character to terminate the string. Yeah. This is not the sugariest way to do string literals, but it works. It's easy enough that I don't want to do the effort to implement anything better right now. So, yeah. Yeah, that's I think a pretty good demo of the TMA16. Actually, why don't we see what happens if you intentionally cause a stack overflow? So let's just type B until, yeah, there we go, stack overflow. So we push more values onto the stack than it can fit. And so what's going to happen is there's a bit called the stack flag, which has just now been set to 1. By default it's 0, but it gets set to 1 if there's a stack overflow. And that doesn't stop the machine or anything. Program execution will continue normally, but you can read the stack flag to see if there's been a stack overflow and change your program's execution based on that with conditional jumps if you want to. But if you don't do anything like that, then program execution will just continue as normal. And you can also reset the stack flag, but this program doesn't do that. So yeah, that's the TMA16. TMA stands for Thoroughly Minimalist Architecture, by the way. And 16 just means 16-bit because it's a 16-bit computer. And yeah. So my GitHub that's the URL on my GitHub account. So follow me there, star my projects, fork me, whatever. And if you enjoyed this video, then like and subscribe, or don't if you don't want to. Yeah. Bye.